Thank you for coming for this talk. I'm Harshit, and I've been with MySQL. I've been maintainer for Vitess for as long as it has been to CNCF. And and today we are going to talk about how Vitess achieves atomic distributed commit using the plain vanilla MySQL. And everybody knows what atomic commit means. Like either you get everything or you get nothing. And we're going to talk about how we reached here, what was the background, how was the different transaction mode that had evolved over the years in Vitess. And then we'll go deep dive into the implementation details about how we did it. So we have like the best. First, we started with something called the multi-commit, which is essentially a best effort commit. Like if nothing goes wrong, then you'll get the fully committed data in your system. And we commit the transaction in a very specific order. So if anything fails, we are able to tell you, okay, what shards the data have been committed successfully, which shards that still have the non-committed data. So the users of Vitess have been known this, and they have like written in the application side code, okay, how to really roll forward or roll back if there's any failure that has happened. And also they have like written application logic that they do only single shard, because in single shard you get the full asset guarantees. So they have ensured consistency by just doing on single shard. And we have been very vocal about it, and we have been told that, okay, you should design your schema and your sharding scheme in such a way that most of your crucial workloads just go into single shard, and so that your transactions remain with asset guarantees. But this is not the case. What we did, we went ahead and made one more mode, which we call the strict single mode. In this case, Vitess ensures that if your query goes to multiple shards, then it fails the query and roll back your transaction upfront. And this has helped a lot of users to fix their workflows and understand, okay, something has gone wrong, which didn't want to intend. And then they have fixed their sharding scheme or the schema management, and then they have made sure that their transaction remains in single shard. But this is not enough, and because when you have sharded, you also want like indexes, which are globally secondary indexes, which means you want to query using your secondary index, which is available across shards. And in fact, just inserting into your main table, you'll end up inserting into a secondary table, which is your secondary index, and that can also again now span in multiple shards. So it's not like even if you have restricted your workflow to be single mode, but sometimes your data itself, because of the secondary indexes, it will go into like multiple shards. And we want to have a feature where we can ensure at least your indexes are consistent, even though your data is going cross-shard. So the actual data is going still in single shard, but because the data is indexed, the index data is going in cross-shard. So what we did is we didn't go and implemented like a very bulky algorithm over here. What we did is we use a very alternative and careful locking mechanism and transaction of sequences, how you first insert data in your index, like the secondary index, and then you insert data in your main table, and then how the commit flow works. So that ensure that your data is still consistent, and you still get the consistent guarantee of doing the index lookup first and then going into the right shard. So this gives you the performance and the consistent index guarantees, and still we were able to say that your transaction is still single shard, and you will get the asset guarantees doing your main workflow will still remain asset because you're going only single shard transactions. And there have been like blog and design doc about it, and you can actually read how we really implemented this in Vitess, and it's available on our website. But this is not enough, right? Like you know that things can still fail, and even though application owners have to write sometimes very complex logic, it's not always possible to really do the roll forward or the roll back if anything fails. So Vitess needs something which actually solves this problem for you, and they need a mechanism like to really understand that there should not be any partial commits in your system. And for that, we actually then go ahead and then we finally implemented the support for atomic distributed transaction commit, and we are using the two-phase commit protocol. I'll briefly touch about what this protocol is. I think everybody just knows, but still, and how then we adapted and modeled so that it is seamlessly integrated with Vitess. So we'll go through all the steps and how the workflow works with Vitess, and we'll show you how we really achieve this. So just a quick overview. So in to-phase commit, there's something called transaction coordinator, which is the one your applications talk to. And then the application sends that, okay, I'm done with everything. Now I want to commit the transaction. The first thing the transaction coordinator sees is, okay, which are all the resource managers which have opened these transactions on, and it sends a prepare to it. And once the resource manager receives a prepare, it either responds back with a success or a failure. And then when the transaction coordinator receives success, then it goes and do a commit. If it receives one of them, if it receives a failure, then it says, okay, we have to roll back the transaction, and it rolls back on all the resource managers. And accordingly, when all this is complete, then accordingly the transaction coordinator returns as a success or a failure back to the application. So if you look at, there was a prepare phase that was introduced. So any database which really says, okay, I have implemented prepare protocol, there are certain guarantees that it has to provide. Okay, this database saying that, okay, I actually have this protocol implemented, so you can use it. So what are the guarantees we'll look at that needs to be there if somebody is acknowledging that I do prepare? And the first guarantee is like it cannot abort the transaction once the prepare is completed. So it can't go back and just say, okay, I can't acknowledge this transaction anymore. And same is once you cannot abort the transaction, you also can't refuse a commit. So if the transaction coordinator says that, okay, now you have to commit, then that resource, that database who acknowledges the prepare has to commit. There's no reason that it can say that, okay, I can't commit. And the third thing is when there's a crash happened, then when that resource manager that comes back, it has to reinstate your transaction to the same prepared state it was on before the crash happened. So if these three guarantees are met, then a database can call it out and say, yes, we support the prepare protocol. And let's see how MySQL fares with it, and what all is needed for Vitess to also say that we can actually say the prepare protocol works within Vitess. So the first one is if you look at like MySQL transactions has already an interesting property, which it says that like if your statements have been fully executed and fully it has executed successfully, which means the next step is eventually like saying commit or rollback. Then the chances of transaction being aborted is almost minimal. Only thing that has happened is like if the connection gets closed. And if you look at the MySQL connection timers, it's like already the default is already like 8 hours, which is sufficient for not to get the for sufficient to get the transaction completed, because we don't expect any transaction to be open for this very long time. And the second thing is you can't use like a TCP connection, because again there can be network issues which can happen, and that can actually close your connection. So that's the two things that you can't rely on. That you have to be ensured that these two things don't happen, and then you can say, okay, the transaction is most likely not going to be aborted. Obviously there are failure conditions which is not there in MySQL. We'll talk about it. But then the second is the commit. Yeah. So if you look at the Vitess itself does not support group replication. Plus, in group replication, you can have a locking conflict in the commit time itself, because at that time it runs the Paxos algorithm. So at that time, there could be a possibility of having a locking conflict, and the commit could fail. So with Vitess, this becomes a prerequisite that you can't run the TCP connection, and you can't use like a group replication to support it. And the third is, yes, there is no transaction logs that it stores when it does the prepare. So MySQL by itself does not give you the crash recovery that is needed to give you the prepare, and that's what we do in Vitess to ensure that by doing all the three steps, we are able to say that the prepare protocol is supported. And we did everything on top of the vanilla MySQL, so there's nothing code that we have written in MySQL to really support it. So let's look at how this maps to our Vitess architecture. So if you look at this, something called VT-Gate, and VT-Gate is the one which talks to your application, and this becomes the natural choice to call it a transaction coordinator, as everything that the application talks is just to the VT-Gate, and this internally talks to then to to the MySQLs. And if you look at, there's something called VT tablet, which becomes a choice for resource manager, because this is the one which will be holding the transaction logs. It will be holding what has been executed on per shard basis. And when VT says, when VT receives a commit, then it basically tells these VT tablets, okay, now you have to persist this in MySQL, so that so that when a crash happens, then when the VT tablets comes up, it looks at, okay, what are the transactions which are there in the prepare phase, and then it says, okay, I have to first re-prepare them and make it so that these all replay, and then we say, okay, now then the VT tablet will say, okay, these are the transactions that I have replayed, and now it says, okay, now I can start receiving any new transactions. The recovery phase of in the VT tablet itself ensure that, okay, that everything which was there is first applied, and then only the new things come up. So we don't expect any lockings to happen, because already when we executed the query, and we have executed the query successfully, which means we are at the phase where the commit is only needed to be happen. So there is no conflict that is going to happen, and no transaction is waiting to acquire any new logs. So all the logs were acquired successfully. That's why when crash recovery also happens, the VT tablet is able to successfully apply all the prepared transactions, because at that point we don't expect any again conflicting. Yeah.
Just a question, you're talking about crash recovery and everything, that implies you don't change the master when the crash happens, so you don't do failover. Is that correct?
Yes, we're going to failover. Yes, because it's persisted during the prepare, so it's available at the other replica, which will become the primary. So at that point, it will
reapply.
Yes, we're going to reapply that on here.
Yeah, so if when you do a transaction on the primary, you also prepare it on the replica in the VT tablet in case it fails.
Yeah, so that is the guarantee. You can do it with the replication. We say you can use semi-sync, so that in semi-sync at least you have one more replica which has that log, and when you do switchover, like if your primary goes down, then that replica will have those logs available to reapply and prepare it to the state it was before. So this is how it fulfills the third requirement, and that's how we complete, saying, okay, all the prepare guarantees are met, and this is how we continue forward and say, okay, now because we know that the prepare guarantees are met, we can actually implement using Vitess, and we can do distributed transactions with Vitess. We will go into now how the commit flow actually works when the VT receives the commit, what all steps are taken to look at it. So what happens here is, if you look at when the commit is received, VT first does this. What it does is, okay, these are in that transaction. It says, okay, what are the shards that are involved, and then it chooses one of the shards as its as it's to store the metadata. Basically, if you look at it, like they have to store what is the transaction metadata, and the transaction metadata is like a place where it tells, like, okay, these are the participating shards in this transaction, and what is the state of this transaction. So this is the important information that the VT has to hold. So what VT does is, it doesn't hold by itself, but it assigns one of the participants, and that's what that participant will store that information along with the DT ID, like the distributed transaction ID. So at VT we generate a unique distributed ID. So for that transaction to be assigned, and that gets stored in one of the participating shards. So we call a create transaction record API on that, and that stores it, and it's persisted in a separate independent transaction.
Quick question: is this limited to shards in the same key space, or can it?
No, across shard, any key spaces. Okay. It's So what we do while generating the unique IDs, like what we do is we use the key space and the transaction identifier and a ID number, so that becomes unique across any key space or shard. So that's how we solve that problem. And and so that is GTID and the participating shards, and the transaction state is being stored in one of the participating shards. So that's how the create transaction record works. Once that is success, then what it does is, on the other remaining participating shards, then it sends a prepare API. So in that prepare API, what it first does is it moves your active transaction for that transaction. It moves them from the transaction pool to the prepared pool. What it does is in Vitess, there's by default, there's something called transaction timeout. And we don't want, once your transaction is prepared, we don't want that timeout to happen. So that's why we move it to a different pool, which is out of the scope of your transaction timeouts. So once that is done, what then it does is whatever the queries that were executed on that shard get persisted in the database. And if that gets successful, then the prepare will return back to the VT gate. Okay, it's successfully prepared. And now you can go ahead and take whatever decision you want to take. So, yeah, and if that steps fail, then the VT gate has no option but to take a rollback decision only. And based on that, also because we are moving from one pool to another pool, you can actually limit the number of prepared transactions you want at certain point in time in each shard. And so, but what will happen is it will then fail your prepare and then you will eventually roll back. But at least you are limiting how much you want distributed transaction to happen in your system. So that can be a limit that you can impose. So once prepare is successfully received by VTGate, what VTGate does is, okay, now I have to just do and commit everywhere. But before it does commit everywhere, what it has to do is, it will execute, first it will do, it has to first store the commit decision. So it sends commit decision to its where it stores the metadata, and what that metadata does is it updates the commit decision to that metadata, and along with it, it also commits the open transaction itself, which was there as part of that transaction. So if that is stored successfully, we know that the commit decision is also stored, and now the decision cannot be changed. So if that is a success, then VTGate receives it and it says, okay, because that API got success, and then it says, okay, now I have to go ahead and now do commit prepared everywhere. So in the rest of the participating shards, it does go and do the commit prepared. The commit prepared is also something similar, where it as part of the active transaction, what it does is it deletes.
That's because the prepare and the commit prepared, you actually write into those shards some data then.
In commit.
Yes, when you're doing the prepare and the commit prepared.
So in the prepare, what we do is we store the transaction we store the statement that will execute as part of those transactions.
So you're actually writing into each of the other shards to do it. Okay.
Yeah, that's what will help in doing the crash recovery.
Okay.
Because if you don't write it, then we don't have the
Unprepared, you commit something in, you commit transaction log.
Yeah, as a separate independent transaction. I was mentioning then, sorry. Yeah, so in prepare, we do it. Whenever I call it independent transaction, what we do is we do a begin, execute a query, and then we commit. But it's an independent transaction apart from your active transaction.
So basically, you build the recovery in replication
Yes.
in a transaction log that you commit yourself.
Right.
Okay.
Yes.
And if the prepare fails on a single shard, does it hang or is it?
No. So if any of the prepare fails, you'll get, so VTGate will receive that, okay, the prepare has failed, and then what it does, it will send rollback prepare. So I'll go through all those steps as well, what we do.
Are you using the XA stuff?
No, we are not using exit. We are not
They
using.
build their own Excel.
Yes. This is what similar exit is also doing in the end. Yes. There are some issues with exit. We can go and talk about it later if you want.
Because XA doesn't work in replication, so they have to build their own XA in replication.
Yes. Okay. Start commit. Yes. I think this one is covered. I already talked about it. Yeah. In commit prepared, right? So on the shard that was selected as metadata manager, where your transaction metadata was stored, is conclude like that has done the start commit. So we know the commit decision is stored. And now for the other shards, we are going to send commit prepared. And in this commit prepared, so it also does delete of the transaction log along with saying, okay, along with committing the active transaction. So that becomes part of part of doing the start commit. Like we delete the record because we don't need it anymore, and we do the commit of the transaction itself. And once that is done, we just have to now conclude. So to the one method, we call it metadata manager, which is storing the transaction record. And what we do is it then says, okay, now I have to just delete the transaction record anymore. I don't need it because it's already resolved. So obviously there can be failures at a lot of steps. So even create transaction can fail, start commit can fail, prepare can fail, any of these steps can fail. And if you look at it, if create transaction fails, then you don't have anything to really look into. You just roll back the transaction and you're done. And if prepare fails, then also you have to, then essentially it's like very simple. You just have to say, okay, I have to, okay, I'll go through it what prepare, if you are in the prepare button. Okay, let's go into this. This is something we have in VD tablet. What VD tablet is checking is, are there any long running, or are there any prepared transactions which are pending for a very long time? And if it is there from a very long time, then it reports to VDGate, okay, there is something that you have to look into and conclude those transactions. So if you look at when we did if you look at here in the create transaction, we stored some information which is about the DT, the ID, and the participant and the state. So there can be 3 states at a certain point in time, which can be a commit, rollback, or a prepare. So I'll go in the reverse order. Like, so if it's commit, then what happens is VTGate knows that, okay, I have no option but really to commit, and at this point it also knows that the VD tablet's job is to be always in the prepared state, because that's what the failure recovery is. That whenever anything has failed on the recovery itself, it will say that I have prepared and I'm now available to execute something on these prepared transactions. And so VDGate role is to look at what are the participating shards and say, okay, now go ahead and just do commit on all the participating shards. Once that is done, then it says, okay, now I can conclude. Similarly with the rollback, because the rollback decision is stored, then what it does to do is, okay, I just have to go ahead and roll back on all the participating shards, and once that is done, then I can say, okay, now I can conclude. But with the prepare, now there can be a race, because there can be an active VTGate who's trying to say, I want to commit and I want to store this, but then it has been doing nothing for a very long time, so don't know what that VTGate is in which state. The other VTGate is saying, okay, I got something that I have to resolve and it's in prepare. So first thing that it does is, okay, I have to store the decision, and the only decision that this VTGate who is trying to resolve the transaction can make is rollback. And then it says, okay, I have to go and now set the rollback. So if it is successful in storing this rollback decision, then it says, okay, now this is success, so I know what I have to do. And then it goes with the same flow of rolling back on the other participating shards, and then eventually conclude the transaction. So that's how the flow, yeah.
So if VTGate actually has no state, because that's
Yes.
fine, okay, so
Yes.
presumably if the VTGate dies and either another one or something within the VTGate, the coordination of that will detect anything that's missing and then clean up, I assume. Is that correct?
Yeah, so with this design, there's nothing stored in VTGate, so everything it has to get.
Clean up something that's intermediate from a transaction that's partially processed.
Oh, sorry, can you say that?
But I'm assuming that if you're part of the way through committing a transaction, VTGate crashes.
Right.
That could happen.
Yes.
Then somehow the rest of Vitess will detect that and then clean up the partial.
Right. So this is the transaction resolution watcher which runs on each VD tablet,
Yeah.
which is keep looking on what are the prepared transactions which are there and which have been there for a very long time. So it has like a time thing that, okay, if it more than 15 seconds, then it will tell the VTGate, okay, VTGate, these are the DTID that it's not resolved, and then it says, okay, I'm going to now try to see what is the current state, and according to these states, these are the steps it has to take.
Okay, and if it sees VTGate disappear, then it probably eventually
Yes.
roll them back.
Yeah, so for commit and rollback, it's straightforward because it knows that it's the decision that has already been made, so it has to just comply with it and do it on all the participating shards. Only with the prepare, it has to ensure that this decision is now stored and then it can move forward.
So all this information is in the sidecar,
Yes, so,
Metadata, right?
so in VD tablet, we have something, the main database, and then there's a sidecar database which is there, which is again same MySQL. Yeah.
Okay.
So which is storing all the transaction log and the transaction metadata, and that's what it's used to do to actually watch on the which are the prepared transactions which are pending.
Yeah, so one of the DT tablet is like stores your transaction metadata,
Yes.
right? So the DT gate knows which one, but if the DT gate fails and the transaction is taken over by another DT gate, how does it discovers this fact?
So one thing, if you know, the notification happens from VD tablet to VT gate. So it knows which one is storing the transaction metadata. But the other thing is the DTID itself contains that information. Because the DTID itself contains key space and shard as part of the DTID, like the distributed transaction ID that we have. So both ways it's discoverable, which is the one which is storing the metadata.
And the client knows that.
The VT gate knows it.
Yeah, but if the DT gate crashes,
Right.
the transaction needs to be taken over by
Right.
another DT
Right.
gate. How does that other DT gate rediscover?
Yes, so in VT tablet we have something called that's what I told, like we have the watcher which is there in VT tablet. And VT tablet will notify to all the VT gates that this is pending. And then one of the VT gates will pick it up and then resolve it.
So the VT tablet that has the metadata is the one telling VT that you need to resolve it.
Yes.
So where the information comes from is the VT tablet where the VT needs to ask for further information if required.
Yeah, somehow you have two transaction managers. You have the VT gate.
Yeah, it's only VT tablet is only the watcher.
Yeah.
Which is watching.
Notification. It's like
It's
notification
not
from
only.
the-
Yeah. So we have already like called health streams in VT tablet, and what the VT gate already watches. So that health streams will tell like which is primary, which is replica, and a lot of other things. What is the replication lag and stuff. This also is a kind of information that also sends. Okay, you have some pending transaction that somebody has to look into, kind of. Yeah. Right. So yeah. So I already talked like we prepare what happens. So if you look at like how we have implemented, there are some. It gives us like how we molded the prepare protocol to how it suits us and in Vitess, and this gives us some of the benefits, which is like if you look at the commit that happens, right? So at the commit time we take a decision whether it is single shard or cross shard, and so there's actually zero impact on single shard transactions because VD gate at that point decides, okay, it's a single shard, so I will just send commit and not follow any 2PC path. The other thing is obviously we talked about like is the transaction coordinator here, like the VT gate is stateless because it doesn't store by itself the metadata record, and so any VT gate can come up and resolve any open transactions, and because it doesn't store the information by itself, it actually does one more clever thing. It assigns one of the participating shard itself as a metadata manager. So we avoid the prepare phase of doing it. So it doesn't have to store the transaction logs and it doesn't have to do moving of your active transactions in the prepare pool for the metadata manager, because this is the one which is controlling. Okay, you have this much time. You either commit or whatever you want to do, but this stops. This also gives you that okay, your 2PC transaction will also complete within a certain time. Either it will be a commit decision or a rollback decision, but time is still limited because this is the one which is also storing the decision itself. So you have only certain time where you want to complete it, and you're also avoiding any additional writes of the transaction log in the metadata manager. And this is still following the same isolation guarantees that you get with the multi-commit, because we just we still want the read scalability to happen before we actually. We want the reads to be still scalable without we actually make so the isolation is still relaxed and we are giving only the read committed isolation, what you get with multi. Only thing is now your reads are not getting logged because we are not waiting for anything to really commit and then you are going to read something from it. Yeah.
So one of the things that Vitess was to certainly to help scale out reads, also to increase your data set sizes. right? If you do cross shard rights because of the way that these things, presumably that also impacts your rights scalability because you're adding extra rights over to all the shards because of that. So presumably you still need to try to avoid this, otherwise you'll impact right performance heavily. But if you don't do this, there's only a few percentage of your right workload, then you don't. There's not such.
Right. That's why I said you can limit this, and we don't want people to fall into like doing multi-shard commits.
Okay.
We still want people to follow that. Try to
Use the right.
Yes. They should still write their schema in such a way that it should be single shard. This is something additional guarantee now you get because now you don't have partial commits anymore in your system, and you'll still get like if you really want your reads to be consistent, then you can obviously go for like the for update kind of way of locking the rows which you want to read, and that in that way you'll get the isolation, the guarantee that you want with your application.
I don't understand why it is zero impact on a single shard transaction. Because when that single shard transaction is happening, you don't know if that single shard transaction will eventually become a multi-shard transaction.
So the thing is that we take the decision of whether we need to do a 2PC commit or not at the time that the commit query is received. So we receive the commit.
Yes.
So we know that the queries that have been run so far, whether they're on a single shard or not.
Yes, but
Right.
they're run on a single shard so far. At some point it will be.
No, they receive the commit,
Yeah,
right?
it's time.
So
Yes.
we didn't
Yes.
receive the commit.
I understand that, but like, let's say from point time A to point time B, it's a single shard transaction. And so it's good, but then it becomes a multi-shard transaction.
Okay.
So it means that if that single shard transaction, like a failure happened, you would have had to log all this.
So
Right? You need to remember this in case that shard fails during the.
right, so that information today we itself stored, like, but we don't store it on MySQL. We store it in the memory of the VD tablet, but that is already being done from the day one.
This can be used.
That is what we're doing.
Yes.
So because we already had that information already, even for single shard transactions for visibility, it's not impacting the performance that people were already seeing with single shard transactions because we're not persisting that into the data store. It's not going into MySQL. That happens at the prepare phase, which we take the decision after VT8 knows that it's multi-transaction.
Yes, but
The storing in the memory is still there, and that is has been there from day one itself. It's not something we have introduced now. It was always there. So the impact was always there.
okay,
So there's no impact, new impact, I would say.
okay, so the VT tablet always remembered
Yes.
all that.
Yes.
Okay.
In memory. And now it's persisted into the database when the prepare call comes.
Yeah.
And that only happens for multi-shard transactions, not for single shard.
Okay, so there's no new impact.
No new
but there's
impact.
still
Yeah,
an
exactly.
impact. Well, there was
Yes.
an impact before.
Exactly.
Yeah, okay.
Okay, and with that note, I'll hand over to Manan, who will talk about disruptions and then take it forward.
Thank you so much. Thank you, Harshit, for the introduction. I'm Manan. I'm also an engineer at PanScale and I'm a maintainer as well for Vitess. And the part that I'm going to take you through is something that we've already discussed a little bit in the question answers, which is how Vitess ensures that the guarantees that are supposed to be required from a two-phase protocol are actually met. We all know that when you're running a distributed system, multiple things can crash. We've talked about VT gate crashes, we've talked about VT tablet crashes, but there are a bunch of other things that can happen online DDLs because we'll need to change your schema and all of those. So this part of the presentation is going to deal with some of those things. I will skip over the content that we've already talked about as part of the question answers, but feel free to ask me questions if required. The picture here is a little bit of a joke here because we basically wanted to imagine our distributed transactions like a tree standing in a storm, that even if an earthquake or lightning strikes, the guarantees that the 2PC transaction has should still stay firm. So this part of the presentation is about how Vitess ensures that the guarantees required by 2PC are met in the face of disruptions. The first one we're going to talk about is MySQL restarts. And what happens when your MySQL restarts is that all your ongoing transactions have been dropped, which means all the transactions that we've already prepared against that MySQL are gone. For resolving this issue, what property we use in Vitess is that MySQL always starts in a super read-only mode. In the myCNF and the myinit files, we always make MySQL start in a super read-only mode in Vitess. So when a MySQL restarts, we know it's a super read-only mode and it won't accept any more writes until it transitions to a read-write state. And before we do that, before users are allowed to run more writes to that MySQL instance, we transition to an intermediate read-only state, and within that read-only state, we redo all the prepared transactions using a DBA connection. So And the DB, again, we already talked about how the metadata is already there in the transaction because we're using semi-sync. So you already have the metadata in the sidecar DB for those prepared transactions, and you redo them again, you open those transactions again.
So you have MySQL super only, but are you somehow prohibiting the use of set persist super only? Because if you store that set persist super only is 0,
Okay.
then it doesn't matter what you put in the configuration.
This is basically like because Vitess is not something that we run, like users have to run Vitess. It's an open source project. So people can choose different configurations, but this is one of the limitations of using atomic transactions, that we require you to always keep that configuration in MyCNF, that MySQL starts in super read-only mode. It's like an additional layer of security.
You need to prohibit the set persist.
Yes, that super read-only has to be required. Same way that we have other restrictions where you need to be running MySQL but only through sockets and not TCP. This is one other restriction, that you have to have the same thing. It's a default that Vitess bundles in with, but you should not be changing it basically to getting the performance, actually the correctness, not even performance.
Also, this is a safeguard because if everything,
Exactly, this is a safeguard. You always want to have that in place.
yeah, if everything goes through the VT tablet, it wouldn't be that.
Exactly.
Right.
And a very similar solution is what we do for VT tablet restarts as well. The property here that we use is, instead of being read-only, we use called a serving state. So VT tablets have a very similar property. Instead of being called a read-only state, it's called a non-serving state. And when a VT tablet restarts, it again starts in a non-serving state, which does the same thing. It prevents write queries from going through, not until it's in a serving state. And we do the same thing. Before it transitions to a serving state, we check, are there any prepared transactions in the MySQL metadata that we don't currently have open, and we open them again. And finally, VT-gate restarts, which is one of the easiest ones because we already talked about it. There's a transaction execution watcher, and VT-gates are stateless. So even if a VT-gate crashes, VT tablet just through the health stream tells a different VT-gate that you need to resolve this, and they pick them up. The other set of disruptions that we're going to talk about is online DDL, reshard, and move tables. And these disruptions talk about because you're running a distributed system, you will eventually need to change your schema. So you will have to run an online DDL to change that schema, or you will want to change how your data is sharded. So you run a reshard, or you want to change the table where it's existing in any key space. So move tables. And all of these operations are first-class citizens of Vitess. So we would want that all of these continue to work, and they continue to work with atomic distributed transactions without having any consistency failures. So to that end, we've added some kind of coordination between these 2-3 different systems of Vitess so that they work well together. For online DDL, the only thing that we need to worry about is the cutover phase. The online DDL itself might be long-lived, but that only is copying data from one table into the shadow table with the changes that you've requested in the schema. For that, it's kind of orthogonal to atomic distributed transactions, which will continue to go into your main table. It's only the cutover when you're switching the two tables around that we need to worry about atomic distributed transactions. And we cannot have any prepared transactions that are dependent on the old schema when that cutover happens. To tie everything together, we use something called query rules in Vitess, which we already had, which we were using for buffering these queries. So during cutover, you still wanted to buffer queries, write queries that were coming in to the VT tablet. So we use the same query rules. What we now do is that when you add that query rule during the online DDL cutover, we prevent any new atomic transactions from happening. The prepare phase itself will fail. And then once we've added this query rule, we wait for all prepared transactions outstanding that are there to have committed. So essentially, this is kind of a stop the world scenario where we're saying when the online DDL cutover happens, we want to stop all atomic transactions, let the cutover go through, and then re-enable them again. And this is not really an issue because the online DDL cutover itself is super fast. It happens in a few seconds. So for that duration, we are able to stop the atomic distributed transactions just for that small period.
When you say stop all the atomic transactions, distributed atomic transactions, you mean those that correspond with that specific table?
Yes, that's a good point. I forgot to mention that, but yes, only for the specific table. So the query rules that we have are based on each table. So if the atomic distributed transaction is not touching that table, they're independent, they continue to go through. And we have a very similar solution. Again, we use the same query rules for move tables and reshards as well, because the difference here is that move table, for reshard at least, it's like the entire shard itself is splitting into 2 different parts, which means that we have to do it for all the tables and not just one specific table. So that query rule is not table specific, it's across the entire VT tablet. And we use the same thing for this solution as well. Now, one final thing that I want to talk about while talking about disruptions is the VT tablet state diagram that we follow. Most of it is something that we've already discussed, how rollback and everything happens on the VT tablet. One thing that I do want to talk about is the checking of the type of failure over here. So if you look at this flowchart that starts in the top right, after the commit redo logs have happened, we prepared and we receive a commit. If the commit succeeds, everything is good. We just need to delete the redo logs and everything is happy. But if the commit fails, we would be remiss as engineers to not imagine a scenario that we've not already added code for. So if the failure happens, let's say it's because MySQL crash or because whatever, something happened that we know how to solve, we'll be able to check it and we'll say, okay, this is a failure because we know how to handle it, and we'll handle it. We'll do the redo, prepare logs or whatever else we need to do, and everything will work. But if it is a situation that we've not encountered before, that we've not thought of, that hasn't happened to us so far, we still want to check that code path and we still want to have checks in place so that the user is not caught off guard. At least they have a way of knowing that this has happened. They can rectify it the way that they want to. So we've got this code path as well, which says that, okay, this is something new. I don't know how this happened. Let's say we got a duplicate key error. Although that should never happen. Let's say we try to redo the logs, but we did get a duplicate key error. In that situation, no amount of redo will help because that write will continue to keep failing. So what we then do is we mark it as an unretrievable failure and we bubble that up to the user and wait for the user intervention to happen for them to fix things, file a bug report, and then conclude the transaction. Yes, please.
So there's the MySQL restart, which is MySQL restarting on the primary. And
Yes.
I guess a failover is kind of a twisted MySQL restart.
Exactly. Yes.
Where you first need to wait
Yes.
for replication to catch up and then do the same.
Yes, PRS, ERS, both of them, because they wait for the MySQL to be caught up. They're like same situations for MySQL restarts. We handle them the same way for atomic distributed transactions. And this is actually also a good segue for us to talk about what the users see, like what insights they have into atomic distributed transactions that are running, because they need to be able to figure out that something has failed. They need to know that they have to take some action, which brings us to the next topic of monitoring. And the first one that we're going to talk about is the VT admin UI, which is the administrator page that that Vitess has. Over there, we've got a specific page for in-flight distributed transactions. And here you can see the transactions that are currently running. Like the commit has been issued, but not yet completed across the shards. So you'll see the state that they're in, the DTID, and this is the DTID that Harshit was talking about. That we've got the key space, we've got the shard ID where the data is stored for that transaction, and then the specific UUID that we have, which makes it unique across key spaces and shards. And then we've got the participating shards that are running as part of this atomic distributed transaction, the time that was created, and a few actions that the users can take. If they click on that DTID, they get a little more information, which is what state it is in, and also individually what each of the shards is doing, whether it has committed the transaction so far, whether it's prepared, or it has failed. All of that will show up here. For the transactions that have committed, because we've already deleted the redo logs, there's not much else to show. But for prepared and failed transactions, they'll have the exact statements that were there. Because we have it in our metadata, we show it to the user as well, that these were the writes that happened as part of this transaction that has failed. Again, this is something that we don't expect users to be able to run because we don't want them to run because we don't expect everything to work, but it is still there in case something goes wrong and they need to file a bug report. They'll be able to see the writes and they can choose how they want to do it. They can either do these writes as a separate transaction and then mark the transaction concluded, or they can choose to ignore the writes if the writes are ephemeral and are not required. Now, the other type of monitoring that people have is that another use case we wanted to support is that when people are running transactions from the VT gate connected through the MySQL client, let's say that they run a commit, but they get an error saying that it timed out or whatever. For that error, they're not ever sure whether the transaction actually committed or did it roll back or is it in the midway state. So when they run a show warnings command, they actually get the DTID itself back for it, which they can parse, and then use show transaction status for that DTID, which will give the same information that is available on the VT admin UI as well. The same we will also do through the VTCTLD client. So there are a bunch of ways of getting this information out of the system for the users to look at. We can talk about the metrics and stats as well. So I'm going to go over this a little quicker than I was hoping because we've got a little paucity of time. So here we just have two metrics. One is about the timings of how long the commit mode took, and we have it across all the three modes. So there's a single mode, multi-mode, and 2PC, and you can compare that. If you move from a multi-mode to a 2PC mode, then you can see what kind of a performance difference you're seeing. This is more of an insight into the performance of the two-phase commit so that people can make a more informed decision. The commit and resolve is just a counter for the transaction that got failed when a VT gate was unable to commit them, and the transaction resolution watcher had to pick them up. We've got similar metrics on VT tablet as well, but the query timings are, instead of being for the entire commit, they're split across individual phases of start, commit, start, resolve, because this helps us debug further into which phase was taking longer if required. And the unresolved gauge is again very similar, that the VT tablet crashed for whatever reason and the transaction had to be redone. The final thing that I wanted to talk about is testing. Working on any of the projects that have such hard guarantees that have to be met, one thing that you need to be sure of is the testing strategy has to be in place to ensure that everything works as expected. The challenges that we had is that we wanted to add disruption code, so all of this disruption handling code, and we want to test all of it and what happens in those situations. Now, one thing that's happening is that we're actively adding code to VT tablets so that they can handle the errors that happen internally without needing to surface anything up to the VT gate. But that also means that it's super hard to test the code on VT gate in the case for the situations where VT tablet does throw that error, because we're actively adding code to prevent that situation from happening. So to test all of this code, we needed a reliable way to actually inject errors into the system at different points in time, because we want to check what happens if a transaction fails after it has said that it is prepared. Although again, we don't expect this to ever happen, it still would be, we still want to test it what VTGate would do in this situation. So to do that, we added something called, we use a go build stack tag that we've added. So there are two files here. If you look at the left file is called debug2pc.go and the right one is production.go. And if you just look at the first line across the two files, there's a go build tag on both of them. First one says that it's only supposed to be built if the debug2pc go build tag is specified, and the second one in all other cases. And there we just have this one constant in both the files, debug2pc being true in the left one and debug2pc being false. What that allows us to do is that this is a code from VTGate, a snapshot from the VTGate code. And once we do a tablet gateway create transaction, we actually have an if block for debug2pc within which we check, do we need to fail at this point in time? Now for the binaries that are built for production, debug2pc is false and it's a constant that's set to false. What that means is that the compiler can throw all of this code away and we do not have any production penalty for it. But for the debug code that we're using for testing, debug2pc is true. So we have after each step, do we need to fail all of these checks? And we can control at what point this transaction fails by synchronizing from the test using environment variables, files, writes, or whatever else that we use. Sometimes even the context, where we just pass the information into the context. And this allows us to inject errors at different points in time across the code base, whether it's VT tablets, VT gates, or not just injecting errors, but also delays. Because within that check test failure, we can also have delays as well of time but sleeps to ensure that even if atomic distributed transaction takes longer, let's say more than 20 seconds, online DDL and all of these don't cause issues with that. So we built a comprehensive testing suite. Using unit testing, we added disruption handling code, and for that we use the go build tag to inject delays. We added miscellaneous tests for end-to-end tests for like metrics, UIs, all of the other things. And the final topic that I want to talk about is the fuzzer test. So me and Harshit had also previously worked on a project for MySQL foreign keys, implementing support for that in Vitess. And we had used fuzzer testing for that as well. There we would just run random DML queries, and in the end, it was super easy to check that everything for foreign keys was holding, because you can just check whether there are dangling rows or not. Like if there is a row that doesn't have a the parent pointer to it, then you know that something went wrong in that system. But it's super hard to do that for atomic transactions, because if you run random DMLs, how do you know that in the end everything was atomic or not? There's no check that we can run in the end just from database state to know that the transactions were atomic. So that end, we added a fuzzing testing strategy of our own, which restricts the kind of DMLs we're running in the transaction. So what we're doing now is the initial setup is that we've got 3 shards and we've got 2 tables, an insert and an update table. And we've got multiple threads that are running atomic distributed transactions and another thread that is running disruptions. All the disruptions that we talked about, we've coded them all up, PRS, ERS, anything that you could think of, be tablet crashing, MySQL going read-only in the between. So all of that, and then each transaction is doing specific type of writes that I'll just talk about using an example. This is the initial state that we've got. We've got three tables because 3 shards and 2 tables, the insert and update table. The update table initially is initialized with just a value of 0. So what each transaction does is that it inserts 1 row in each of the 3 shards in the insert table, and it updates the row in the update table. The update value is randomly chosen. So this is a rand.int that we call. So let's say for this transaction, the first thread inserted 1 row. So the thread ID would be 1 because it corresponds to that thread running that transaction. And it would update all the 3 values to 23 because that's the random value that it chose. Following this, if let's say that the second transaction runs, but it runs from the second thread that's running the transaction, it would insert this row, something like that, thread ID 2, and the update value will become 123 if the random value it chose was 100. What this means is that this 123 is kind of like a checksum of all the transactions that this individual shard has accepted. Because each transaction has a random value that's generating and updating on all the 3 shards, this becomes a checksum. And this is just a log of all the transactions that each of those transactions accepted. The auto increment column is not something that we specify. We just let MySQL do that because this gives us basically an explicit ordering at which point the transactions were committed on that shard. Now, the kind of failures that we check for is, let's say that the transaction was not atomic, the second transaction that ran. The database state that you would see would be something like this, that there would be only 1 row there and the update value would not match the other 2 shards because that 100 is not here. So these are the 2 checks that we use to know whether the transactions were atomic. One, that all the shards accepted the same amount of transactions, which would be the count of the rows in the insert table, and also that their update value matches because that is the checksum of the updates that they actually did accept, of all the transactions that they did accept. Now, this is not a perfect strategy. There can still be situations where the test passes, but there was a failure in the system. But the premise is that it's so rare, and if there is a consistent failure in the system, eventually there would be a test run that will surface that problem, and we'll find it out. So while this is not the perfect way to test everything was atomic, this is still deterministically good enough that eventually we'll find a problem in the system if there was one. We also check one more thing. This is the final situation that we check for, is that if the commits were out of order on a specific shard. For that we use the auto increment value. So we order by the auto increment value on each of those shards, and we check whether the thread IDs were the same, especially because all of them are conflicting on the same update rows. So the writes have to be perfectly ordered because they're all conflicting writes. We take this a step further. This example that I have over here is actually somewhat simplified from the actual fuzzle that we implemented. Instead of just having these one row in the update table, we call this set of 3 rows as one update set, and we've got multiple update sets. So we don't just check that everything has to be perfectly ordered on the insert tables. We check for each update set, everything has to be perfectly ordered. And we've got save points and few other things that we added just to make the system more complicated, and check it responds correctly in those situations as well. And finally, we have a couple of feature enhancements that we've thought of but not yet implemented. The first is read isolation that obviously Harshit talked about. And the second is we don't currently have any kind of distributed deadlock avoidance. So you could potentially run systems where you've just got a write pending on both the shards, but it's blocked on because the other shards are not yet committed. So we don't do that right now in Vitess, but we potentially will. Thank you so much. And you have questions? Also, out of time.